If your team's aiming to boost their GCSE grade this year, you don't need to do it alone. That's exactly why I've created the Level-Up Launchpad. Hi, I'm Andy, and after 12 years of teaching and helping thousands of students jump one, sometimes even two grades in just a month, I know what works, and parents tell us it's the most supportive GCSE space online. Inside our Launchpad, you'll find short, powerful video lessons, live support from real teachers, and a community of students who are all working towards the same goal: better grades and more confidence. Here's Becky, one of our brilliant science teachers, breaking down GCSE Chemistry in a way that just makes sense.
Hi guys, I'm Becky the science tutor, and today we're exploring rates of reaction. So basically how fast or slow a chemical reaction happens. So if you've ever wondered why some reactions like fireworks happen in a flash, or others like rusting take a long time, in this lesson we'll look at the factors that affect the rate of reaction, from things like temperature to concentration and even the use of a catalyst. So by the end you'll be able to explain why reactions speed up or slow down and how you can control them. Let's get started. Okay, so for a reaction to happen, two things must be considered. First of all, those reactants have first of all got to collide, and this is about collision theory. The second factor is, do those particles have enough energy? And this is our activation energy. Okay, now I'm going to say the word collisions quite a lot throughout this session. Okay, you'll be sick of hearing it by the time that we've finished. Okay, so if we look at the first reaction, you can see that we've got two reactants and nothing has happened by the end of it. So the first thing that's got to happen is that the reactants that you are reacting together, first of all, they've got to collide. If you never put the two reactants together, if you have two separate beakers, then of course they're never going to react. So first of all, they've got to collide. And the second part is that they have to collide with enough energy. Because what could happen is these particles could simply collide and just bounce back off one another and nothing happens. So in scenario 2 that you can see at the bottom, if we look at our products, we've got different products to the reactants that we put in. So that means that 1, they must have collided, and 2, they must have collided with enough energy for that reaction to happen. And if you've watched the previous video on endo-and-exothermic reactions, you know that we've got to put that energy in first, that activation energy, to break those bonds to then reform it and make our different products. Okay, so let's go through and have a look at some factors that can affect it, what conditions we can change, and how that means the reaction changes its rate. Okay, so the first one is based around the concentration of a solution, and it's the same in theory for the pressure of a gas. Okay, so if we increase the concentration, okay, the rate of reaction is also going to increase. And the reason for that is that when we increase concentration, we're increasing the number of particles. And if we increase the number of particles, then it's more likely that they are going to collide. So we're going to get increased collisions. And a way that I sometimes get students to kind of visualize this is if we think about a classroom of students and you were to just be simply walking around the room, you might not collide with anyone because there's plenty of space within that room. But if I brought in 2 or 3 more classes worth of students, there's simply more students, and so you're more likely to collide. Therefore, that would increase the rate of a reaction. If we're thinking this in terms of the pressure of a gas, what we do is when we increase the pressure, we decrease the amount of space that those gas particles are within. So if we had that just one class of students walking around the classroom, but if I put a divider up in the room and made the room only half the size, yes, there are no more particles, but you're in less space, and therefore the chance of collisions is increased. Okay, so whenever we're thinking about a condition, what we need to think is, does it make more collisions? So does the frequency of collisions increase? Or does it mean that they collide with more energy? And if your answer to either of those is yes, then your reaction rate is going to increase. Okay? Now what I'm going to do today, and I want you to really focus on, is the language that we use in the answers. Okay, because remember we talked about particles can collide but not actually react. So when we go through these model answers, you'll see that we use terms like the successful collisions. Yeah, because when they actually collide and react, that is a successful collision. Now what you might see in lots of these questions are little graphs like this. You are often asked to draw a second line on the graph to show a higher or a lower concentration or something like that. So if we look at this one, let's say that that green line was already drawn for you, and the question might say to you, draw a second line on the graph to show the progress of the reaction at a higher concentration or a higher pressure, whatever the context of the question is. Now key things is that we're still going to start at 0, because there is going to be no products at the start of the reaction, because we might not have even introduced those two substances yet. If they don't mix them together, they won't react. And what's going to happen is we can see that because it's at a higher concentration, we've got more particles, more collisions, and therefore it happens faster. So that second purple line is steeper because the volume or the mass of the product is being formed quicker, so we get a steeper line here. But one of the key things to remember is that we're still going to level off at the same height, because we're not making any more. Remember, this is the total mass or the volume. We can't make more mass, we're just going to make it faster because the rate has increased faster. Okay, now this shape of graph pretty much relates to anything, whether that's temperature, concentration, because again, if we increase temperature, reaction goes faster, so we get a steeper curve, still going to level off at the same point because we've still got the same amount of reactants going in. Yeah, so we can't make more product, we just make it faster. Okay, right, so let's have a look and explain some of these questions then. So this is a very typical question. This is a required practical where you are reacting sodium thiosulfate with hydrochloric acid, and when you react those two together we get solid sulfur being formed, and so that reaction solution goes cloudy. So this is a nice simple way. It's a straightforward practical because all we do is place that on top of a cross and we time how long it takes till you can no longer see that cross, because the more that reaction progresses, the more sulfur that is made, the cloudier it becomes, and it becomes to a point where you can't see that cross anymore. So what we can do is just very simply time how long it takes for that cross to disappear. And that's something that we'll go into more detail in the practical in another session. Here we're just looking at the theory behind what's going on in those particles. Okay, but you do see that as an example quite a lot. So here it says, from the investigation, the student correctly concluded that as the concentration of sodium thiosulfate doubles, the rate of the reaction doubles. Explain the student's conclusion in terms of particles. So what is it that's going on? Why are they correct? So we've got 3 marks available. So for the first mark, we want to be recognising and identifying that there are more particles in there, or if you said they're closer together, yeah, just because there are more. So we can say that there is an increase in the number of particles. So increase in concentration has increased the particles. We could say like something in the volume, something like that. Yeah. Gonna get your mark from recognising there are increased particles. So because there are more particles, well, what happens? So what we've got now is we've got the frequency. So how many? The frequency of collisions increases. I put more people in a room, there's probably going to be more collisions. Okay, so yes, the reaction is going to go faster because we've got more particles in there and more collisions. So now we've got to explain, well, as the concentration doubles, the rate of reaction doubles. Well, yeah. So as we double the number of particles, we've got double collisions. So as the particles doubles, the collisions double. Okay. So that's for our concentration. Now I've put you one in here. Sorry, I can move it on. Relating to pressure. So this is a very similar sort of idea. Yeah, but remember this is because when we increase pressure, we've not got more particles, we put them in a smaller space. But again, because they're closer together this time, because they've got less space, we're still going to get increased collisions. So here we've got the pressure of reacting gases was increased. State the effect of increasing the pressure and explain your answers in terms of particles. So we've 3 marks available. So we've got 2 parts to this question. We've got state and explain. So state the effect of increasing the pressure. That is going to be that the rate increases. Okay. Now we need to explain in terms of particles. So why? This is because the particles are closer together. Okay, and then I often say, yeah, so the particles are closer together, so what? So the frequency of collisions increases. And if we've got more collisions, trying to write and talk, if we've got more collisions, we're more likely for those to react together, and therefore the reaction goes faster. I've completely lost my train of thought now. There we go. Okay, so let's have a look at the next one. So here we've got temperature. So temperature is the most effective way to increase the rate of a reaction, because what we've got going on here is we've got twofold. If we give the particles more energy, then they're going to be moving faster. So the scenario that I often use again with class of students is that if you were just simply walking around the room, you might not collide with anyone. But if I gave you lots of sugar and gave you lots of energy and said sprint around the room as fast as you can, you are more likely to collide. So because particles are moving faster, we've got more chance of collisions, and because those particles are moving faster, they've got more energy, and because they've got more energy, they're more likely to collide. Remember, sometimes they can collide and bounce off one another, but if they're hitting harder, it's more likely to be a successful collision, not just a collision. Okay, so if we increase temperature, we increase the rate. Why? Well, we've got more collisions, and we've got more energy. And if you think about reactions that you've carried out in the lab, if you want to make them happen faster, think how many reactions we simply just heat up using the Bunsen. All we're doing is we're just getting that reaction going. We're making those particles move around more, and they're moving with more energy, and therefore more likely to react. Okay. So again, let's use a question as an example. So here we've got something different. We've got a reaction where we are collecting the gas that is being produced. But the question is asking us, an increase in temperature increases the rate of reaction. Use your knowledge of particles to explain why. 3 marks. Okay, so why? What's going on? So we can say, first of all, the particles have more energy, or that they move faster, whatever works for you. Okay, so because they've got more energy, particles collide more often. So we've got more collisions, and we've got more of those collisions are successful. Just remember, it's not just about making more collisions, it's that we're getting more successful collisions. Okay. Okay, final one then. So what about the surface area? So when we increase the surface area, we're often making our reactants smaller. So you might have done this with something like large marble chips or limestone chips, smaller chips, and then in a powder. So all we're doing there is we're increasing the surface area. Now when we increase surface area, it just means that we've got more area exposed where collisions can actually happen. Because here you can see that what's happening in like little scenario 1 is that only that middle particle is actually going to collide. The other 2 have missed. Whereas if we make them smaller, we're essentially making more of them, therefore more collisions. Yeah, it's all that's about. Sick of hearing me say collisions now? So if we increase the surface area, it increases the rate. Why? Well, essentially we get more collisions because we've got more area exposed where those collisions can occur. Okay. So let's follow our same pattern. Explain in terms of particles and collisions the effect of increasing the surface area of the marble chips on the rate of reaction. Okay, so just 2 marks for this one because this is what we were just talking about. So what does it do? Well, we're going to get an increased rate. So something about it increases the rate. Yeah, and why? Because it says explain. Well, because we've got more frequent collisions. That's nice and straightforward for that one. And the final thing that we need to take into consideration is the use of a catalyst. So if you've watched the endo and exothermic reaction video where we've talked about the energy profile diagrams, here we've got exactly the same process. And in here you are often just asked to draw that second line. So our endo and exothermic reaction topic. Often links into rates of reaction because the examiner can ask lots of different bits. So it could ask about a catalyst and then bring in that reaction profile diagram. So that's why it's important that you know how to label it, so that then if you get something like this, you know straight away what you're doing with it. So the purple line is the activation energy, and when we use a catalyst, it lowers that activation energy. So what that means is some of those collisions that weren't successful, we're now lowering that energy value, so they don't have to collide quite as hard to react. So if I lower that value, then actually some of those other collisions might then be successful collisions. Okay, so let's have a look at a style of question for this one just to finish us off. So here we've got the reaction profile diagram. That's where I mean that it could quite easily bring this into rates of reaction. And part D, complete the reaction profile diagram. So we've done that in terms of in the endo and exothermic. So if you're unsure how to do that, go check out that video. So here we want to label the activation energy. So that is from our reactants up to the peak of that graph. So we label activation energy, and then we need to label the reactants and the products using the names of the reactants and products. Okay, so it tells us that information is there. So it represents a profile of a catalyzed reaction between ammonia and oxygen. Yeah, so we're actually going to write these on, ammonia and oxygen, and then we need to know what it is that is produced between those. So the same for our products. So our products are nitrogen monoxide and water, and it doesn't matter, I'll put you one of each, it doesn't matter whether you put like the words or the symbols as long as they are correct. Yeah, so we've got to have like H2O for water, because we've got to have the correct products. Yeah, and so we're completing that graph. So part E is then, how would figure 2 be different if no catalyst was used? So this is using a catalyst. Remember, the catalyst has brought down the activation energy. So if we didn't use a catalyst, that peak, yeah, this line would be higher. Yeah, now we don't have to draw it on, I'm just drawing it on to show you. So it says here, the line would reach a higher peak. Okay, like I say, if you want any help with reaction profile diagrams, go check out the endo and exothermic reactions video. And as always guys, if there's any questions, then please do get in touch and I will happily answer those for you. Otherwise, I'll see you next time.
And that's just a glimpse of what you'll find inside the Level-Up Launchpad. If your team wants expert teaching, proven strategies and the motivation to succeed, join us today. Just click the link below to get started.